Okay, recording.
So, welcome everybody to this new session of the Chilean probability seminar. So we have the pleasure to have with us Andrés Contreras. He's a Chilean guy who has never been in Chile, if I'm not mistaken.
Yeah,
He
no,
just
I was born there, but then I left when I was two. So
yes. So you were not here when you were conscious. So you will
exactly.
probably have to visit soon. So he's now in Chicago, trying to understand these things we saw with Alexandra last time, which is these LQG surfaces, but adding the curvature part. So you have to remember your differential geometry course. But I think he will teach us. So the floor is all yours, Andres.
All right. Well, thank you for the invitation, obviously. What a pleasure to be here. So today I'll be talking about Gaussian curvature for LQG surfaces and also Gaussian curvature for random planar maps. Right. So first, let me start by explaining what LQG surfaces are.
Okay.
So first, let's look at canonical random curves. So first, let's think about what's the most natural way to define a random curve. So if you think about it, there's not really a right notion of a uniform uh, measure on curves. So we need to define this some other way. One way you can do this is by discretizing, and then it actually makes sense to take uniform measures. So you can uniformly sample a path pj with a j going from 1 to n from paths in Z2 with a length n, starting from the origin. Right, so you just have this path in Z2. You can interpolate linearly between two vertices, and then you can take some sort of limit of this. And as a lot of you probably know, this converges to Brownian motion. And so this is sort of the way that you construct a canonical model for a random curve. Right, so now you can also ask what happens in higher dimensions. So first, let me just review a couple of properties about this curve here, though. So this is the canonical probability measure on continuous curves. So it's canonical in many senses. So first of all, it has infinitely many self-intersections. It's no longer differentiable, and it's sort of a universal object. So it shows up as a limit of many different models for curves. And so there's sort of general theorems that tell you that if you have a random curve with certain general properties, then it should converge to Brownian motion. Right. So now we think about what happens in higher dimensions. Let's just restrict to random surfaces first. Higher dimensions are even harder. There's what's called Liouville quantum gravity. So this is a thing that already appeared in physics literature in the 80s, but this was only in physics, not anything really rigorous. It has connections to conformal field theory, to string theory. That's like on the physics side, and in the more mathematical side, there's stuff like planar maps and random permutations, stuff like this. Okay, so usually it's related either because it's some model of these physical things, or as limits of these planar maps, or sometimes related to these random permutations as well. Right, so I mentioned these planar maps. So these two pictures over here, can you guys see my mouse?
Yes.
All right. Yeah, so these two pictures here are actually simulations of approximations of LQG. So by planar map up here, all I mean is an embedded graph, which might have different weights sometimes or might not have weights. In this case, we just have two different models of triangulations. So the one up here is the uniform triangulation. And the one down here is actually just a sphere packing, which generates a graph. So you can see that the circles sort of join in triangles. And so this also gives you a triangulation. And you can prove actually that these models converge to LQG. So first of all, I guess you should say what LQG is actually defined to be, and there's multiple definitions of this. And also, I guess I should mention that there's multiple topologies that you can assign them. So you can have LQG on the plane. You can have it sort of on a sphere. You can also have a quantum cone or other things like this. As I said, there's multiple definitions. You can define it to be the scaling limit of random regulations like these, or sort of a definition already in the continuum is as the exponential metric of a Gaussian free field. Right. So let me first introduce what a Gaussian free field is. So you have a centered Gaussian field with this covariance structure given by log of z plus log of z w plus log of 1 over the distance. So this uniquely determines what your field is like. So it's Gaussian at every point, and this tells you what the covariance is like. Now this thing isn't actually well-defined pointwise. It's just a generalized function, and this generalized function is called the whole plane, GFF. Right. Now, as I mentioned before, for different variants of Liouville quantum gravity, you sometimes want to consider different topologies, like the sphere, for example, or you can look at the quantum cone. And these require usually different variations of this Gaussian free field. Right. So in this case, there's the quantum cone field, which is the same as your Gaussian free field, but minus a gamma log singularity. Right. So this is the formula for your phi. Okay, now I mentioned that, well, this is a surface, and so things that you would like naturally are stuff like a measure or a distance metric or stuff like this, right? And so formally, you can define what the Riemannian metric is. So for gamma between 0 and 2, you see that a gamma LQG surface is formally the surface with Riemannian metric given by e to the gamma phi. Now, as I mentioned before, phi isn't actually a well-defined function. It's only a generalized function, and so taking e to the gamma phi is not exactly well defined. But still, you can sort of make sense of this via approximations. So as I mentioned before, you can also construct this alternatively with limits of random planar maps. So you need to scale it, and then you get some space, and you usually get this LQG surface. And you also get a measure, which is formally defined to be e to the gamma phi dc. So again, this is not well defined, but you can make sense of this by some sort of smoothing procedure. So you can take your GFF and average it with either the heat kernel or some other smoothing. And for each one of these smoothings, the Riemannian metric actually makes sense, and so does a measure. And then you try to extract some limit and say that it's tight and say that it's unique. Right, so first, let me introduce a couple of important constants. So let d gamma be the fractal dimension of gamma LQG. So this is a constant that actually has some decent bounds for it. And let c be gamma over d gamma. So these are constants that only depend on gamma. And also let q be gamma over 2 plus 2 over gamma. Okay, then recall that the LQG metric exists. So this is due to Ding, Dubeda, Dunlop, and Falconet. Right? So this is sort of what I was mentioning before. You can prove that these metrics associated to these smoothings are tight. So you can actually talk about subsequential limits, stuff like this. And then Gwynne and Miller showed that the subsequential limits are actually all the same. So they're uniquely determined. And the way they did this is that they sort of wrote down a set of axioms that a subsequential limit should satisfy. Then they proved that these axioms uniquely determine your field. Right? So these axioms are stuff like invariances. So first, d phi is a length metric, which means that, well, it's a sort of regular-ish metric. You take the infimum over all possible paths between 2 points. You take the length of that path, then the infimum of that is the distance between the 2 points. D phi is local. That is sort of self-explanatory, just that it depends locally on the pair of points that you're taking the distance of. And it also satisfies vowel scaling. So this means that it's invariant under this thing here. So if you add a function f to your field phi, then the way it changes your metric is in this way here. So you have e to the cf dot d phi. And this is the notation I'm using to denote this thing here. So you take the infimum over all possible paths between 2 points, and then you take the integral of e to the f at the point of the path. All right, so it's some sort of point-wise weighting of your metric. Right? So this describes exactly what happens to your metric when you add a function to the field. Right, there's also stuff like the coordinate change. So if you have a dilation and a translation, or rotation as well, then you can see what your metric changes like. So d phi of ru plus z plus rv plus z is the same as the distance between u and v, but where you've changed your field by the same scaling and translation, and also you've added q times log r. So q here is the same constant I defined before, which is gamma over 2 plus 2 over gamma. Right. In fact, this thing is slightly more general. You can have the same identity here for other conformal maps. So you can put like d phi of some conformal map C of u, comma C of v, is equal to the distance between u and v of phi composed with psi plus q times log of the derivative of psi. Right? Okay, so there's many properties that are known about LQG, which well, I mean, usually they're related to stuff like the dimension or stuff like the geodesics. So for example, there's this property called confluence of geodesics, which was also proven by Gwynne and Miller, which tells you that sort of the geodesics tend to coalesce. And well, this is not really expected of a smooth Riemannian metric. This is strictly about LQG, and sort of the intuition is that these geodesics have to pass through like very, I guess, low weight places that are surrounded by high weight places. And so they sort of have to go through these little tunnels and yeah, they start to come together. There's also properties about the Hausdorff dimension. So there's short bounds for it as well. But in a way, all of these properties are sort of first order. So you might try to think about higher order information. So if you went back to like a smoother Riemannian metric, which this isn't, you can try and think about stuff like second order information. So things like curvature. So this is one of the first things that you think about, like the together with the second fundamental form and stuff like this. And so it would be natural to try and define this for LQG, even though LQG isn't actually smooth at all. Right? And so we do this. So remember that if we have a smooth Riemannian surface with metric e to the f dx squared plus dy squared, then the Gaussian curvature is given by this. So this is the formula for the Gaussian curvature for a conformally flat metric. Now, in the case of LQG, remember that our metric is e to the gamma times phi dx squared plus dy squared. And so it would be natural to define our curvature just by plugging in gamma times phi up here. Right, so we get that our curvature is defined as k sub phi equal to gamma times Laplacian of your field phi over 2 times e to the minus gamma phi. All right, there's a problem here though, since again, this isn't well defined, since phi is a generalized function. And for this, actually, you can't directly take limits and make sense of it. So you have minus gamma here, right? So the way you do it is that you can define this weakly via this formula here. So for any coupling
There's
supported,
a question.
Yeah.
So before, just from the field before, so you were, so I'm not that used with Riemannian geometry. So you think about it coming from the metric or coming from like from the measure in a way, because like so you wrote it with gamma. So does it come naturally from the measure, or it should come more naturally from the metric, this curvature?
It comes from the Riemannian metric. So the Riemannian metric has gamma phi here.
Yes.
The actual distance function requires you to have a different constant, which is this xc that I defined above.
Yes.
But sort of the Riemannian metric itself has e to the gamma phi. So it just comes from like what the Riemannian metric should be.
Okay.
The measure is
So,
sort of related to
but
what
in yeah, but in what comes, maybe I'm just going for spoilers, but you are going to get a key there.
Oh, sorry.
What is the right? So I'm just going for the spoilers. So is it going to be a gamma for like the gamma Liouville measure, or is it going to be a key for?
Oh, actually, it's
which
going
is
to
the
be
right parameter?
It's actually gamma. So
Okay.
as I was saying, you want to define this weakly somehow. And so the way you do this is by integrating against the Liouville measure. So if you have a smooth coupling supported test function, then you can integrate your function f against your curvature. and then sort of integrate by parts. So actually, let me sort of explain what this competition is. So let me pass to my iPad. The idea is something like this. So you can
Yes.
define what you guys can see, right?
Yeah.
Okay, perfect. So you can try and integrate a smooth test function f of z against your curvature g phi of z, and then d mu phi. Right. So remember that we were trying to define this curvature formula, at least, as gamma times Laplacian of your field phi over 2 times e to the minus gamma phi. Right, and then recall that mu h is at least formally e to the gamma phi dz. And so you actually pick this gamma here so that it sort of cancels out with the Liouville measure. So these, oh, whoops. These formally cancel out. And you're left with the integral of f of z is gamma Laplacian phi over 2 dz. And so after integrating this by parts, you would get the integral of Laplacian of f of z times gamma over 2 times phi dz. All right, and this is actually well defined. You're just integrating some smooth function against your field phi. Right, so now going back to the right. So this is how you define the curvature. So you always need a smooth coupling supported test function to define it. And I guess one thing that you would like, given all the invariances that LQG surfaces satisfy, is that this curvature satisfies those invariances as well. So if you change your field under the same same things as they changed up here. So if you dilate phi and then add q log r, then you still get the same curvature. And this is easy to verify. In fact, if you have any conformal map, then you would have to be applying phi composed with that conformal map plus q times log of the derivative of the conformal map. And when you go back to the definition of curvature, actually the formal definition is enough. When you take the Laplacian of your field, the log of the derivative of the conformal map is going to be killed off since that's harmonic. Right, so it's I guess you need to use the weak definition to actually verify it, but it's not too hard to verify.
A second stupid question, maybe. Is it obvious that such a k exists? Like
yeah, I mean, yes, sir.
Yeah, no, it's just that, like in a way, it's just like a linear story, no?
Yeah, I mean, you can define it as like the linear operator which acts on smooth test functions like this, and that's well defined.
I see. Thank you.
Okay. So remember that I talked about triangulations in planar maps before, and the fact that they can approximate LQG. So now I'm going to talk about a particular triangulation that's going to be useful in the rest of the talk. But first, I'll also have to define a few general quantities in a triangulation. So first, suppose that G is a triangulation. We can define then the discrete curvature as 6 minus the degree. So I can try to explain why this is a natural thing. So let me, again, go to my iPad. If you think about it, oh, it's not. Okay, there we go. If you think about it, you can sort of try to embed these triangulations in space. And if you have 6 equilateral triangles, then this should sort of correspond to the flat case. So this should be considered to be flat. And so you should have the curvature is 0. If you have less triangles, then if you try to embed it in space, then it should sort of curve up. And so if you have less than 6, this should be positively curved. So this should have positive curvature. And if you have more, then when you try to embed it, it sort of curves in a way that looks hyperbolic. And so you would expect the curvature to be negative. Right, so if you have multiple triangles here, then you expect the curvature to be negative. Right, now another way of seeing this is that for any graph, you can assign to each face, I'll say this is the face F, you can assign sort of these artificial angles at each vertex to be whatever you would expect if F is a regular polygon. So you assign the number of sides minus 2 over the number of sides times pi to each of these angles. And then you look at the deviation from 2 pi at every vertex. Right, so here you would have another face with a different number of sides, and maybe another face here. Okay, each one of these has their own angle. And when you add all of these up, you subtract 2 pi from it, or you do 2 pi minus the sum of the angles, and then that's your definition of curvature. Okay, so in our case, we just have triangles, though. So if you have any point, the graph around it should look something like this. So you just have a bunch of triangles around it. And so each face here is a triangle, and so each of these angles is just pi thirds. So your definition of curvature would be 2 pi minus the sum over all the angles at your vertex V. Okay, but all the angles are pi thirds, so this is just 2 pi minus the number of faces times pi thirds. And as you can see, the number of faces is also equal to the degree of the vertex. So this is 2 pi minus pi thirds times the degree, which you can factor out as pi thirds times 6 minus the degree. Right, so since we're defining this up to constants anyway, we can consider the definition of curvature to be 6 minus degree. All right. Now, I mentioned before that these things are, well, when you take limits of these triangulations, you can get LQG. So there's actually this conjecture here that if M is a model of infinite random planar maps believed to already be converging to the gamma quantum cone. So one example of this is the uniform infinite triangulations. And you embed the map in the plane via some reasonable embedding. So you can use something like the tut embedding, or maybe the sphere or the circle packing embedding. Then the scaling limit of these curvatures up here, so these KGs, is expected to be the same curvature that I defined before for LQG. So this thing up here. Okay, at least for gamma equals square root of 8/3, which is when these planar maps converge to LQG. All right, now there's multiple triangulations that have multiple equivalent definitions. So first, let me start with one. First, let lambda be a Poisson point process with intensity epsilon to -1, where epsilon is some positive constant. And then also let L and R be two Brownian motions, normalized so that they both start at 0, and such that the correlation is given by minus cosine of pi gamma squared over 4. Okay, then you can define the Meta CRT map G epsilon, which is a particular triangulation, as the random planar map obtained by mating discretized version of continuum random trees constructed from L and R. Okay, so let me actually draw a picture explaining what this looks like. Okay, let's do this shares. Okay, there we go. So you can draw two Brownian motions on a big rectangle. So this could be L, and this other Brownian motion can be R. Okay, and then you can construct something out of this by discretizing your time interval, and then identifying points on both of the curves. Right, so you identify points this way, and you identify points this way. Right, and so with this, you actually get a tree. And well, before you discretize, you get a triangulation. And the relation for this geometrical picture is the relation that I had on my slides. So it's this thing here. So it's you say that two consecutive points yj minus 1 and yj are connected if the infimum of LT and the infimum of LT in these two intervals, yj minus 1 yj and yk minus 1 yk, is also equal to the infimum of LT in the interval yj yk minus 1. Right, so if this holds for L, you get an edge between yj and yk, and you get two edges if this holds for both L and R. Right, so that describes what the graph is like. There's an equivalent definition in terms of the space-filling SLA kappa prime. So the space-filling SLA kappa prime is a space-filling continuous curve, which you can look at any moment as something that fills a part of the space, and after certain intervals of time, this fills out extra bubbles. Okay, so you can sample space-filling SLA kappa prime independently from your field phi, and then reparameterize it in such a way that the gamma quantum mass with respect to phi is the same. So if you remember, we can define what the measure is with respect to the field phi. And so then you can do a time change parameterization of your SLA kappa prime so that it covers the same mass for every unit of time. Okay, and here we're particularly picking kappa prime equals 16 over gamma squared. Okay, and so the thing is that this gives you an alternate construction of the graph that I described earlier by taking the adjacency graph of these SLA kappa prime cells. Right, so you can define the graph with vertex set lambda, where two vertices yi and yj are connected if the corresponding CRT map cells eta of yi minus 1 and yi and eta of yj minus 1 yj share a non-trivial boundary arc. Right, so let me switch again to my iPad to draw a picture so that you can get an idea of what it looks like. So if you stop at any time, you can see what the curve eta looks like. So remember that sort of the points are traced in a certain order. So you can make it so that this part over here is what's covered in the past. This is in the future. And this right here is, let's say, eta of some time interval yi minus 1, comma yi. Okay, so then in each interval of time, this curve eta fills out some region, and the regions all touch each other or something like this. I guess I shouldn't have drawn that there. And then you can look at the adjacency graph of these. So each one of these corresponds to a different interval defined by the points in your Poisson point process. And so you just say that these pairs of cells are connected to each other. As you can see, just by the geometry of this picture, you can see this always defines a triangulation, at least almost surely. Right? And the important thing is that these two definitions give you something with the same law. Right? So this is due to Duplantier, Miller, and Sheffield. This is this whole mating of trees theory. Okay, so we'll use these two definitions in the talk. I mean, in some places it's more convenient to look at it as just a graph, sort of abstractly picked, or sometimes it's more convenient to use it as the adjacency graph of SLA kappa prime. All right, so now our main theorem of myself and Gwynne is the following. So you can let G epsilon be the epsilon Poisson mated CRT map, as defined above, with either definition. Then for any smooth coupling supported function f in CC infinity, we have that with probability 1 or going to 1 as epsilon goes to 0, the sum of this test function against your curvature is of order epsilon to the O of 1. Right, so you might think first, okay, well, this is nice, but why is this useful? And what does it actually tell you about the curvature? So the thing is that if you try to bound it by brute force, you would say, okay, so the sum has epsilon to the minus 1 vertices more or less, since it's the number of points in your Poisson point process in a given interval. And so you're adding up things that look more or less independent over epsilon to minus 1 vertices. You would expect the sum to be of order epsilon to minus 1/2. All right, and this is a lot bigger actually than what we're saying, which is epsilon to the O of 1. So this sort of tells you that there must be some non-trivial cancellation that, yeah, tells you that there must be something going on, and that these curvatures are actually not really independent from each other. All right. Now, a natural question is whether there is actually a scaling factor necessary in this conjecture that I made above. So if remember I said that if you scale your discrete curvature somehow, then you would expect this to converge to the LQG curvature that I defined at the beginning. But we don't know what this scaling factor would be. And our theorem is telling us that this is of order epsilon to the O of 1, and so the scaling factor should be of that order as well. So you might think that there actually isn't an epsilon dependent scaling factor that you need for this. And the answer to this question is probably no. And an easy reason to see this is that if you make a local change to your graph, then your sum against this test function increases by some fixed amount. And this fixed amount should somehow be killed by your scaling factor, because in the limit, you shouldn't see this local change. All right. Okay, now we can also define the total curvature on any region. So you can sum up these discrete curvatures on some region in the plane. Particularly here, we're looking at the total curvature on a CRT cell. So you can take a fixed CRT cell, like a eta of -1, 1, or something like this. And then you just add up all your discrete curvatures inside this region. All right, so you just define your discrete curvature kg epsilon c as the sum of your discrete curvature over all points in C, which are vertices of your graph. Okay. Then we also prove the following. So you can take this total curvature on a CRT cell, normalize that by epsilon to -1/4, and this converges to something explicit. So you can define this this random variable B as follows. So you sample L first according to the law of the boundary length of a mated CRT cell C. Okay, so remember that you had this CRT cell eta of -1, 1. You look at the length of that, and then you sample theta according to a Gaussian distribution with mean 0 and variance equal to this length that you sampled earlier. Right, then this random variable B above and theta have the same law. Right, so you have this more or less explicit description of what the scaling limit of the total curvature on CRT cells is. Right, now, something you might notice is that up here, I said that this was epsilon to the O of 1. Well, in the theorem for total curvature in CRT cells, you have the scaling factor epsilon to a -1/4. You might wonder why this happens. It seems like this should be because of the roughness of CRT cells, but this tell you one thing, which is that probably not all curvature definitions are compatible. So if you think back to Gauss-Bonnet, the total curvature in a region should be the integral of the geodesic curvature on the boundary. And so if the total curvature is well defined, then you can sort of define what the geodesic curvature is. And so if you could define actually both the geodesic curvature and the Gaussian curvature, that these should scale differently. And so maybe it's not actually possible to define them simultaneously, given the different scaling that are necessary. All right, so let me try to explain a bit about the proof.
And just to come back to the other one. Yeah, so I really had a problem understanding what B was. So is there a...
Yeah, sure. So first you sample L according to what the length of a meta CRT cell is. So remember that you have like eta of -1, 1, and then it has a certain length that you can sample L according to.
And L is the line, L is the curve.
L is this L here. That's something that you're sampling according to the law of the boundary length of the curve, or of the cell, sorry. Right, so then this is some random variable, and then you can sample theta according to a Gaussian distribution with variance L and mean 0.
But right? Okay, so maybe this is where I'm getting lost. So this boundary length sometimes can be like not a random function, no? It can be not like a probability measure. It could be from a Lebesgue story, or I'm getting wrong here. So
I mean,
when you have
it's a
these stories. Okay. So sometimes you have this integral over R that always confuses me. But
No,
this
I
is
mean,
not what's going on here.
no, this thing is well defined. This is a well-defined
Okay.
distribution, and then you can sample your theta according to that, or your L
Okay.
according to that, and then you sample theta to be a Gaussian distribution with mean zero variance L, and then yeah.
Okay. Now I get it. Yes.
Right.
Sorry.
Yeah, no problem. Okay, so then this tells you what B is, and this sort of tells you explicitly what this scaling limit is. All right, so let me start looking at the summaries of the proof. So for the first theorem, the one about the sum being epsilon to the O of 1, as I mentioned, there has to be some sort of important canceling going on so that it's of lower order than you would expect. And you can actually see this in the discrete case. So you have this convenient cancellation when computing the sum. And it's due to like a combinatorial identity. So first, if E is an edge with starting vertex v1 and end vertex v2, we define the discrete gradient to be just f at the end vertex minus f at the starting vertex. Then we can actually rewrite our sum up here as the sums of discrete gradients of f. Right, so you can assign orientations to every edge of your graph g epsilon, so that for any completely supported test function f, the sum of f of v times k g epsilon of v can be split into these two sums of discrete gradients of f. Now, the reason why you need to split it into these two sums is because these correspond to the edges coming from L and R. So if you remember the definition of our triangulation up here, we have this relation that has to hold for either L or R or both. And so you can separate your sum into the edges corresponding to when one holds for L and when it holds for R. Okay, and so these things you split off into different sums and you bound separately. So we'll just consider each one of these sums separately. They're bound in the same way. So let's, for example, consider this one here. The second ingredient is that you can actually map each vertex v to 4 different sort of canonical edges, defined by taking either the rightmost past edge, the leftmost past edge, or the rightmost future or leftmost future edge. So what I mean by this, going back to our picture, whoops, go back to our picture about what the SLA curves look like. This was what our SLA curve looked like before. So here, if you're taking this vertex v, you can look at the let's say rightmost left cell connected to it, which would be this one. So this edge here would be E arrow past left, right? This one right here is the leftmost, or sorry, this is right. This would be the leftmost past edge. So this edge right here would be E past left. And then similarly for the ones in the future. So the other two would be these two. Okay. And so you can split off your sum into sums of these discrete gradients along these particular edges. All right, so this is what I'm saying here. Your sum of discrete gradients can be split off as the sum of these discrete gradients along these 4 canonical edges. All right, so the above part sort of is the cancellation. I mean, in each cell, you're taking these discrete gradients, which you would expect to be small. Now, the point is that you actually need to bound each one of these sums. First, you want to conveniently split these gradients so that things are sort of local. So each one of these discrete gradients you can split off into the part that is inside the cell and the part that is outside. Yeah, actually, maybe I shouldn't have gone back to the slides. Let me explain this. Let me start from a clean picture. So this is your T cell. This is eta, and we have these adjacent cells here. Remember that we have 4 different edges, and for each one of these edges, you can split it off into two different parts. So the part that is inside, the part that's inside the cell, and the part that is outside. So you can take the 4 parts that correspond to the parts inside. So it would be these things here. Right, then you only consider these when you're looking at this particular cell, and the other pieces you add to the other when you're computing the part of the sum that corresponds to the other cells. Right, now remember that there's other parts that are coming from other cells. So if you were counting instead the sums of the discrete gradients from this cell here, then there should be an edge that's going towards this point here. So you can sort of assign orientations like this. So these are outwards pointing. And there's an inward pointing edge, which is coming from another adjacent cell. This should be via EFL or EFR or something, or one of these 4 labeled edges corresponding to this this edge here, or this vertex here, sorry. All right, so then you can also split this thing here and split this into the part that corresponds to the previous cell that we were considering, and the part that is outside. Okay, so there should also be another component coming from the cell that's up here. All right, and so you can define a new quantity, which is defined to be the sum of these red contributions here, which come from either the cell itself and its 4 special edges, or the special edges coming from adjacent cells that are coming into that cell. Right, and so this sort of depends locally on the CRT cell, which is why we split it up like this. Okay, so then if you define GF to be these red contributions, then you can rewrite your original sum as the sum of these GFs. Okay, so now the goal becomes to control the expectation of the sum of these GF squared. Right, so if you remember, we just want to control the sum, and bounding the second moment is enough for this. All right, so now there's a few steps involved in this. So first, you can rewrite the above sum as an integral. So this will be a lot more convenient later when we're trying to split it into different regions. So we rewrite our sum as the integral over C of GF of xz over the area of your cell, dz. Here, hz epsilon denotes the CRT map cell containing z. So z is just some point on in the complex plane, and each point is contained in some CRT map cell. Hz epsilon is that corresponding cell, and xz is the corresponding vertex to that. So remember that when we constructed this adjacency graph, you could just assign some random vertex inside the CRT map cell, and this random vertex is xz. All right, so now we rewrote this as an integral. Okay, we'll need this piece of notation, which is just for a technical point. So hz hat epsilon will denote the union of all CRT map cells adjacent to the cell hz epsilon, union hz epsilon itself. Right, so if you have this single cell, you basically add on all the adjacent cells as well to it. Okay, so first we'll want to fix these diameters in areas of these cells. So you'll let EJ be the event, or actually the set of Z in C, such that the diameter is between epsilon to the alpha j plus 1 and epsilon to alpha j, and where the area is at least epsilon to the beta, where the alpha j's are a partition of a sufficiently large interval, where where this is between consecutive alphas is very, very small. Right, so inside each one of these sets, you have just points where the diameter is sort of fixed. It's between 2 very close scales, and the area is above something. Right, so these approximately split off.
Andrés here, so this EJ is like our point. So why is it an event? I see like a subset of C.
Yeah, no, yeah, actually it's a subset of C. That's a typo. Yeah, it's a subset of C. And these approximately partition the whole space. So the points that are outside all of the EJs are a very small set. Right? Since you expect sort of the area of the cell to be larger than epsilon to some power, and you're covering a very big interval with the alpha j's, and so you're covering most of what you would get for the diameter of h hat. All right, so this
I see.
Sorry? So this part outside is sort of like
but this AJ, the union of AJ is not the whole space, because you always need this area to be bigger than epsilon to the beta.
Yeah. So it's not actually the whole space, but it covers most of the part. And since you're trying to bound this integral squared anyway, you can allow for like some small error terms, and the complement of the unit of the EJs is one such error term that's like smaller than epsilon to the O of 1 anyway. But yeah, I mean, yeah, you're right. I mean, it doesn't cover the whole space.
Thank you.
All right, so now you can sort of focus on bounding this integral inside each EJ. And so you can try bounding the expectation of the integral of the indicator function of EJ times gf of xz over the area of hz epsilon, all that squared. All right, so note that this thing bounds, if you can bound these things for each j, then adding them bounds the expectation of the whole integral squared, or at least most of the integral in the union of the EJs squared. Right? That's enough to just bound it within each EJ. Okay, so now, as I mentioned before, you wanted to split it or rewrite it as an integral, so you can split it properly now. So you can write the expectation of this integral of this indicator function of EJ times GF over area as the expectation of the double integral where your 2 points Z and W are at distance at most epsilon to the alpha j minus zeta, and distance greater than or equal to epsilon to the alpha j minus zeta, where zeta is some small positive constant. Right, so essentially we're just splitting off this integral squared as the double integral over Z and W, and then we split this into the case where this distance is less than epsilon to alpha j minus zeta, where it's greater than or equal to epsilon to alpha j minus zeta. Right? Oh, and here xz epsilon just denotes this quotient up here. All right, so intuitively, the term where you're on the diagonal, so like where Z and W are close to each other, should be small because the measure of the set where Z and W are close to each other is small. And the other term you expect to be small because the term xz epsilon satisfies these long-range independence properties. So you remember we made the special effort to split off these gradients so that this GF sort of depends locally on your field. So where did I find it? Yeah, so you're to rewrite the sum as the sum of these GFs, where these GFs were the sum of the red contributions, which is sort of local. And so if you have points that are far away from each other, then the GFs should be sort of independent. Right, and so let's actually make this a bit more rigorous. For the diagonal part, if Z and W are very close to each other, then you expect xz epsilon and xw epsilon to be basically the same. You get something like xz epsilon squared, which is the degree bounded by the degree of z squared times the diameter squared over the area squared. Right, so remember that you're looking at the sum of these red contributions, and there's degree of z contributions. And each one of these contributions is at most diameter over area, since it's the discrete gradient of f, which is bounded by the L infinity norm of the gradient of f times the diameter, and then over the area. And okay, so then the degree of z is bounded, since you don't expect points to have very, very large degree. By bounded, I mean something like log epsilon, something like this, which is epsilon to 1 anyway. And also you expect your CRT cells to be sort of round. And so you expect the diameter squared to be like the area. And so this is approximately the degree of z squared over area of hz epsilon. And this degree you can bound by some power, or by any positive power of epsilon. And so this means that the integral in the diagonal of xz epsilon xw epsilon is bounded by epsilon to the 2 alpha j minus 2 zeta. So this comes from the fact that w is constrained to be in a ball of this radius around z. Then times the integral of the indicator function of ej over the area of hz epsilon dc. And since we're in the set ej, remember that the area has to be bounded between two different this is the same as like the diameter squared, which is bounded between epsilon to the alpha j and epsilon to the alpha j plus 1. And so this is approximately epsilon to the 2 alpha j minus alpha j plus 1 minus 2 zeta. And remember that we picked these alpha j's so that these differences are very, very small. And so picking zeta to be like an O of 1 in epsilon, this is at most epsilon to the O of 1. Right, so this bounds the diagonal part. Now for the off-diagonal part, this requires a lot more computations, but the idea is more or less what I said before. So these xz epsilon, xw epsilon satisfy these long-range properties. And so you can actually, after a lot of computations, bound this by epsilon to this 2 times the difference again, plus 1, times the expectation of the indicator function that both z and w are in the support of f, times the indicator function of ej, times 1 over absolute value of z minus w squared. Right, so here you can sort of see already that when z and w are very, very far away from each other, xz epsilon and xw epsilon sort of depend less and less from each other. Right, so you end up getting that this thing is also like epsilon to the of 1. Okay, so then going back through all the rewriting of the original sum, you get that your sum of f of v against your curvature is of order epsilon to the O of 1. All right, so this sort of tells you more or less what the first main theorem is proved. Okay, now for the theorem about the total curvature unless you're a team up cell, there's also a combinatorial ingredient. So you can sort of write this discrete Gaussian. So when you add your discrete curvature on a region, you can rewrite this as the sum of this discrete geodesic curvature on the boundary. So this comes from this identity here. So the total curvature can be rewritten as a perimeter of the boundary minus 6 minus the sum of this exterior degree over vertices in the on the boundary. Right, so then you can rewrite this as the sum of these discrete geodesic curvatures, where these discrete geodesic curvatures are given by 3 minus the exterior degree. This is sort of analogous to the geodesic curvature that you would get in the continuous case. All right, and now we again split this the sum into 4 different parts corresponding to the past left, past right, future left, future right. And so these are the 4 components coming from the boundary of your CRT cell. So let me draw another picture here. So remember that now we're taking the total curvature on a fixed CRT cell. Let's say that this is eta of minus 1, 1. Right, so these denote like the boundary between the past and future. And we have these 4 vertices that appear naturally. So this right here is eta of minus 1. Okay, this is eta of 1. Okay, so then we have these 4 vertices, so eta of 1, eta of minus 1, and the 2 vertices that are at the ends of the boundary between past and future. All right, and so if you remember, we rewrote this total curvature as a sum of these discrete curvatures along the boundary. And so you can look at the 4 sums that are in each of these pieces. So this past right, past left, and future left and future right. All right, so these are treated the same way. So let's just pick one of them and see how we would bound this. Okay, so we split it off into each of these pieces. Now the second ingredient is to use some central limit type theorem with an independence property of these discrete geodesic curvatures along the boundary. Right, so these geodesic curvatures are more or less independent along the boundary, and as you send epsilon to 0, the cells that are on the boundary of this fixed CRT cell eta of minus 1, 1 become smaller and smaller. And so you're adding more and more of these geodesic curvatures, and so you expect that some central limit theorem should tell that this converges. Right. So here's the picture that I was drawing earlier. If you have a fixed interval here, then you get like smaller and smaller cells along the boundary, each one with its own discrete curvature. And then when you average this out by epsilon to the minus 1/4, then you get that this converges to something. And in fact, the epsilon to the minus 1/4 just comes from the fact that you expect around epsilon to the minus 1/2 cells along this edge. Right. Okay, now there's some natural questions that come from this. So I mentioned that we can define this discrete curvature for these triangulations, but I can't actually extract a limit yet. All I've said is that the sum against the smooth test function is of order epsilon to the O of 1. But it's interesting to think about the problem of whether this actually has some sequential limits as epsilon goes to 0. Right, and if it does have a limit, whether the scaling limit is indeed the curvature assigned to LQG. So like this Laplacian of your GFF times e to the minus gamma phi. Right, and also if this actually converges, you might be wondering what the scaling factor is. So I mentioned earlier that the scaling factor is probably not constant, and is in fact going to infinity, but obviously has to be of order epsilon to the O of 1, so maybe it's like log epsilon or something, but yeah, we don't know what this scaling factor is. Right, another thing is whether this k phi is a universal limit. So as I said before, LQG can be written as the limit of many random planar maps, or at least it's conjectured to be the limit of many random planar maps. And in theory, for each one of these, you could define a different notion of curvature. And actually, within each one of these random planar maps, you might have multiple definitions of Gaussian curvature. And so it's natural to ask whether sort of it doesn't matter which definition you pick and which graph you pick, if the limit is always the same, and it's the LQG curvature. Right, and another question is whether there's an observable on CRT maps which converges to the underlying field. Right, so if you remember the definition of the LQG curvature that I was using is this definition here. So actually, we have the integral of the curvature against a completely supported test function is equal to gamma over 2 times the Laplacian of your test function against phi. And so you see that if you integrate by parts to the right-hand side, you get the Laplacian of your underlying field. And so maybe you've picked your f properly, you can extract what your underlying field is. So let me explain this with a computation. So if you have the integral on the complex plane of the inverse Laplacian of f against your curvature, then by definition, this is equal to the integral of gamma over 2 times f of z times, or I guess Laplacian of f times, or no, sorry, just f times your field phi of z. All right, so if you know how to compute this expression here for any f, then you can compute what your underlying field is, phi, weakly. And now if you actually have some sort of convergence of some scaling limit of these discrete curvatures to the LQG curvature, then you would expect something like 1 over a epsilon of the sum of v over vertices of your graph G epsilon of f of v times the discrete curvature kg epsilon of z to be converging to the integral of f of z times your curvature k phi of z dz. Or sorry, d mu phi. What about here? You could replace f by its discrete inverse Laplacian. So you can define the Laplacian of the graph, and you can actually also define the inverse Laplacian just as well. So you would expect this inverse Laplacian of f to converge to the integral of the inverse Laplacian of f here. And then, as I said above, this is equal to the integral of gamma over 2 times f of z times phi of z. So the idea is that even though your graph G epsilon is defined in a very complicated way depending on your underlying field phi, you might be able to recover it by just taking the discrete curvature and summing it against like the inverse Laplacian of some function f, and then taking the limit, and then you might be able to get what the underlying field is from that. Right. So from what I know, it doesn't seem like there's actually any easy way to extract the underlying field from like the random planar map itself. And so this would be a one path to it. Right, so as you can see, these questions are all sort of related to whether this thing converges to the LQG curvature. this question still seems out of reach. I mean, it doesn't seem like it's very doesn't seem provable right now that this discrete curvature converges to the LQG curvature. But I mean, hopefully in the future this can be done and these problems can be solved as well from this. Right. That's it. And thanks.
So thank you a lot, Andrés. So are there any questions? Oh, so someone raised the hand in the CMM. You are clapping, or
Yeah.
you're. Yeah. So okay. So I had one regarding to your last discussion. So could you manage to without? So it's not interesting for this talk, but for getting just the curvature, could you check? Could you check that the integral of like the discrete integral in the CRT map converges to the integral against the Liouville measure? Because that would solve that question, for example.
I mean,
just like a sum. Yeah.
Yeah, I mean, if you have I mean, yeah, like the counting measure on the CRT map converges to the Liouville measure.
Yeah, but
the problem
then
is,
somehow you have your last point, no? Because that's an observable on the CRT map that converges to a Liouville measure, but the Liouville measure determines the field in a non.
yeah, that's the thing. I mean, it doesn't seem very direct how to like extract the field out of the Liouville measure. I mean, there's maybe multiple quotients that you could try, but it doesn't seem like any of these are easy to pull the field out of.
Yeah. Okay, so it's not easy, but it is possible. In a way, you know it is measurable with respect. One is measurable.
Yeah, I mean, so you know it's measurable, but like trying to actually extract it out of observables in it doesn't seem easy. So this like would directly tell you what the field is without having to like pass the measure and then trying to extract the field is out of that.
And if I understand correctly, you believe that the inverse of the Laplacian in this CRT map will converge to the inverse, will converge, or the Laplacian converges to the Laplacian, or the inverse of the Laplacian converges to the inverse of the Laplacian in the natural way. So you don't have some kind of like Liouville Brownian motion instead of having the. So
it's possible.
not exactly the Green's function. Okay.
I mean, it's possible. I mean, we don't know. Maybe you, as you say, you get something like related to the Liouville Brownian motion instead of Brownian motion in the complex plane. I mean, again, we're not really sure. So it might be that these inverse Laplacians actually converge to each other. But I mean, yeah, I mean, either way, it seems like maybe you have to weight it by some other thing. But the idea is that this should converge somehow to the underlying field.
And I have a last question. So can you say something directly about K5? Because you had this really nice definition of K5, but somehow it is pretty abstract. Can you tell us how it looks, and like does it have some kind of integral of the whole curvature? You have.
Yeah, I mean, well, the thing is that we did trying to integrate the whole curvature because we were interested in Gauss-Bonnet and what would happen with this definition of curvature. And it seems like something really finicky happens because when you integrate it, I think you got like 0 or something, which is not what you expect. You would expect it to be like 2 pi if you're in the quantum sphere or something like this, or whatever constant you're supposed to get for the sphere. I forget what it is. But yeah, I guess maybe something is not being weighted properly, like in the singularity. So it seems like the Laplacian of your underlying field phi is very, very singular. So maybe when you actually try to integrate this, it's not 0, and you just get something that's not well defined. Yeah, not exactly sure what else. I mean, the form of it should tell you more or less that in places where the field is very, very convex, then this curvature is very, very large. It's just like the Laplacian of your GFF times the, I guess, like inverse of the measure, if that makes sense. But yeah, besides that, I mean, there's not much that can be said right now, at least, of this definition of curvature. And I think a lot more
I said that
could be
was
said.
the last one, but
Yeah, sure.
I have another one. Sorry. So at the beginning of your talk, you say that there is another object which is natural. So I'm not that well versed in Riemannian geometry. So it's like the two tensor, or so the two field, or I don't remember exactly. So there is another second order operator than what could think about.
I said, for example, like the second fundamental form.
Yeah, that one. So what does essentially mean, and what would it mean in this context?
Yeah, I mean, so in well, the thing is that in this context, you like well, I mean, for like any Riemannian two surface, I guess you can define what the second fundamental form is. So it's just like some form telling you also what like curvature is, but not only Gaussian curvature, it also tells you what mean curvature is, the principal directions. This seems like a lot harder than trying to define the Gaussian curvature. Because, well, in particular, if you had the second fundamental form, you should be able to define what the principal curvatures are, look what the directional curvatures are as well. And this doesn't seem very doable, I mean, because it doesn't seem like you can actually define curvature on single lines properly.
Oh, okay, sí.
But I mean, if you somehow manage to, for example, define the mean curvature, then you could try to use that in the Gaussian curvature to solve for like the main, like the principal curvatures and define the second fundamental form out of that. But yeah, I mean, for now, at least we don't know how to define the mean curvature.
Great. Thank you. Thank you a lot. So are there any other questions? I monopolize the questions. So if not, let's thank Andrés again. And I'm sorry we didn't have your address to send you some coffee.
Oh, no problem.
We should start implementing that from